Hi, I bought 3 exciting products. This one creates big arcs when you press the button here. I just had to get it when I saw Styropyro playing with it. It might look familiar to you, especially if you hold on. Yeah, keep it away from your face. Thankfully, it only creates 1 pulse per button press, and the pulse is super short, so it mostly just, ow, stings. What I was trying to say is that it is just a Tesla coil. Look, if I zap a prototype board, the arcs only move vertically and horizontally. Ow! Huh? Ow! Ow! Why does it hurt out more when it goes through the prototype board? Ow! Yeah, it's not as bad. Ow! I don't know. Anyway, I connected the corner of the board to earth and we should be fine now. Yeah. Maybe don't hold the board with your fingers at all. There you go. See? Of course, the reason is that the holes are diagonally further away from each other. Now, what is it good for? Killing the bugs, maybe? Let's see. Did it actually die? Oh, it's alive. Just shocked a little bit. Oops, I think I reset it now. Let's perform CPR on it. It seems it's coming back to life. It was mostly annoyed. See? Electricity is perfectly safe. Yep, it's perfectly fine now. Sorry, my little test subject. I'm pretty sure they still find it pretty painful, so don't go around bugging the bugs with this thing, even if they bug you a lot. You have to kill something, just kill it, no torturing. Or maybe you can use it as a cool way to turn on your lighter or gas stove. If you can aim the damn thing. There you go. And this is my other toy. Oh. It even hurts less. Ow! What the hell? It was hurting less until it hurt much more for some reason. What was that? Did I accidentally send the arc to the side screws to the circuit that created some low frequency, high voltage thing that shocked me? Yeah, let's not do that. Well, this one can connect to Bluetooth and play music and tones, see? You see it? Nice. So say you can 3D print my torso. What a beauty. Drill a hole through the bottom for the needle, then drill some holes through the ears to connect to the same path. Put this on top of that. Maybe some wires through the ears. Turn it on. Wait. Look at that. Arcs are coming out of my head. Let me run some thin naked wires around it. Here we go. And the third piece of technology I got is this. This is the chipset that you eat that allows the government to track your every move. I'll talk about this later. What are these really good for? Nothing really, except maybe this last chip. I bought these to learn from their designs. Same as how you can learn from my sponsor, Brilliant.org. Brilliant and I collaborated on curating a few series of learning paths which consist of interactive courses and quizzes I personally find useful. Sign up to start learning them for free at brilliant.org/ElectroBOOM. I'm taking the solar energy course and man, I'll tell you more about it at the end. Anyways, I realized I don't need to reinvent the wheel because my fellow engineers in China already spent weeks to design a proper circuit I can learn from. Which I think they learned from Tesla Universe YouTube channel that made a much more massive Tesla coil gun like 10 years ago. Which was featured on one of Smarter Everyday's videos.
Okay, I'm good. It just scared me.
Doesn't matter. The important thing is that we learn the knowledge from each other and do our own thing with it. So, well, let's start from this seemingly boring tiny board. I think it's actually pretty cool. It's what's called a USB-C decoy. It pretends to be a device under charge and commands the USB-C chargers to release the precious juices for us to use. See, USB-C chargers can output different voltages depending on what the device demands from them. And if you plug this decoy into USB-C, depending on which contacts you short, you can get the output voltage you need to power something. Okay, imagine this. You make something that runs on a 12-volt supply, but you want to run it on a battery. That could be a single cell 3.7-volt rechargeable lithium battery. So you need to make a switching inverter circuit. But lithium batteries need to be protected for charge and discharge, otherwise they may blow up. You know, like those old Samsung phones. So now you need a complex protection circuit. And of course it would be nice to be able to charge it through USB. So you give up because your mom never taught you to design this stuff. But you don't have to, because all these circuits already exist in a proper portable backup battery pack. Something like this, with the battery and all those fancy circuits. All you need is this decoy to set the voltage you need. Well, of course it also depends on what your charger or battery pack is designed to output. My stuff can typically output 5, 9 and 12 volts. This decoy is set to 9 volts, and if I plug it in, I get 9 volts. And this one is a 12 volt decoy, and I can even connect a 10 ohm resistor across it, which draws 1.2 amps from it. And the resistor is actually getting warm. What happens if I accidentally short the output? Nothing. Apparently it has protection. It's outputting 5 volts now. Yeah, back to 12 volts, no problem. Suddenly, you can run anything on USB-C, make it battery operated and rechargeable, like my Firefly lantern. I connected the supply lines to the decoy and plug it to USB-C. And there, it starts working. Cool, man. Ooh, nothing blew up. What happened to the boom in ElectroBOOM? To the next one. This thing is battery operated and has a charging port and a knob here to turn it on and adjust the power. Everyone runs it at maximum, I assume. And this is the secondary of the Tesla coil, and according to the text on it, it has 600 turns with a resonance of between 1.2 and 1.4 megahertz. And here's the button, and yeah, actually this is a ground connection that your hand has to touch. Otherwise, it will throw off the resonance. If I don't touch it, see? And if I touch it, so now we open it and see what's going on inside. Whoa, this is fancy looking. See, there is a 3-cell battery for around the 12 volt supply, a big capacitor here to smooth the power supply, 2 transistors to switch the voltage across the primary, which is like a 4 turns of copper on the PCB. And what is this? Do they have their own switching power supply? Let's measure the voltage across that capacitor. Whoa, almost 56 volts? They do have their own switching power supply in here. And most importantly, they generously provided the schematic of the driving circuit. Maybe we can analyze that. Look, they do have a DC-DC converter that creates the 60 volt voltage. So I guess the knob turns on the 12 volt to this DC-DC converter, and at the same time it also controls this PWM signal. Well, I mean, you also have to press the trigger button to create this PWM output. And the PWM signal connects to this point here, and it's not really a PWM, it's like a single pulse with the pulse width that's controllable with the knob. What the signal does is that it controls how long you want the output high voltage to be on, and the longer it's on, the more powerful arc. I would also take this schematic with a grain of salt. Like for example here, instead of this resistor, I would put a diode. You know, when the signal is low, it pulls this transistor down through the diode, which turns it off, and so the entire circuit won't resonate. And when the signal goes up, the diode turns off, so the transistor is free to oscillate. Now, of course, we know the secondary of a Tesla coil resonates at a frequency which is controlled by the inductance and capacitance of the secondary. The current through the secondary is sampled into this connection here through this tiny transformer that provides signals to the gates of these transformers. Since these signals are connected to the opposite sides of this transformer, it means the gate signals are 180 degrees out of phase. This results in only one transistor to be on at the same time. So say if this transistor is on, the current flows through the power supply through these components to ground. And if this transistor is on, the current flows in this direction to ground. So we'll have a sine wave across the primary of the Tesla coil and this capacitor that is controlled by the feedback from the secondary resonance itself. And of course, the primary inductance combined with the values of all these components are tuned to have the exact same resonance frequency as the secondary of the Tesla coil. And you know what happens if you provide an AC across an LC circuit with a frequency that matches its resonance? Its output keeps rising to infinity. Well, ideally, in reality, it is limited by the losses of the circuit. In this case, the rise across the primary results in an even larger rise across the secondary until it arcs, after which it pretty much remains the same for the duration of this PWM signal, after which it turns off. Nice. I should put it back together. Now let's see what's inside this one. Although I expect it to be similar, except that instead of a switching power supply on board to boost the voltage, the adapter already outputs 48 volt DC. Use my Linus driver to open it. But one important thing is that all these devices that create long arcs require a big power supply in them, like 56 volt on the other one, 48 volt on this one. So running it straight from battery is not gonna cut it. Okay, it's interesting. This is the Tesla coil, and it was connected through these holes and the standoffs of the board to the electronics. You may be thinking, how is this a Tesla coil? You may not be able to see it, but this is the winding of the secondary. And I can only see like a single turn of primary here. The coating of the wire is black. I wonder if I can count it. But anyway, this is the output of the secondary, and if you can see it, the other side of the secondary connects to this hole, and the primary connects to this hole and that hole. Here are the secondary windings under the microscope. How did they even make this? Anyway, there seems to be roughly 10 turns in every 2.64 millimeters. So I say somewhere around 130 turns of secondary and 1 turn of primary. Here's the circuit. I'll show each part on the screen. And similar to the other Tesla coil gun, this tiny transformer is for the feedback from the secondary. Let's go analyze the circuit. This seems to be the circuit. First, you have a DC-DC converter to convert the 48 volt to a low voltage that can be used by low voltage circuit. We have an actual PWM circuit that creates a real PWM signal that has a frequency and a pulse duration. You can choose how to control the frequency by this switch switch either through the Bluetooth module by something you play on your phone or through this knob. And the pulse duration is controlled by another knob. By adjusting the frequency, you can play music, and by adjusting the pulse duration, you can adjust the output power. The PWM using this transistor basically turns the circuit on and off at audible frequency. When the circuit is on, similar to that last circuit, the current of the secondary is sampled by a tiny transformer that turns these transistors on and off one at a time. There doesn't seem to be any components to resonate with the primary, so there is just a sine wave across the primary with a frequency matching the secondary resonance held by this feedback loop. That should be all. Let's see if I reassembled it right. What? Yeah, it works. See, we can learn a ton from cool existing designs. So please let me know if you find a cool product and I'll tear it apart and we will learn stuff together. I should make it a new series with a name like Let's Tear It, y'all, or Letitty. Sounds familiar. Anyway, I'll work on the name and you start using my sponsor brilliance.org. Let me tell you about these curated series we collaborated on. I started taking the solar energy series and I was expecting to learn stuff on photovoltaic solar panels. But I'm halfway through the path and I learned so much more. They cover a ton of things like sun rays, power and energy calculations, energy concentration, and much more. And they quiz you every step of the way too. I'm learning way more than I expected. This could be an entire university course. And you can start learning it for free with the 30-day free trial signing up from my link brilliant.org/ElectroBOOM. And then click on the learning paths link in the video description to get to those courses and so many more hands-on interactive courses and quizzes. Brilliant is the best way to learn science, math, and computing easily and interactively at your own pace and comfort on your computer or through Brilliant's app on your phone. And the first 200 of you to sign up using my link will also get 20% off Brilliant's annual premium subscription. So you can keep learning from thousands of courses, which they also add to very often. Keep staying sharp, and thank you for watching.